Hey class, Mr. Bean here for AP Physics. This is a supplemental video for information for you to do some of the simulations. And this is going to be talking about the conservation of energy and ramps. Okay, and so let's see how we might do this. All right, so suppose we have a box here, and this box has some mass m. Okay, and we're going to drop the box to the ground. And let's say we start off at some initial height HO, and the box is going to drop in this direction. And we want to know is what is the velocity of the block uh, right before impact? Okay, what is V? Okay, what is V? All right, so V has what value? Okay, so when we do this problem here, we're going to use a conservation of energy. So we do know that it starts from rest. So kinetic energy initial is going to be 0, and the potential energy is gravitational, and it's going to be mgho. All right, so we release it to the ground here. So at the bottom down here, potential energy is going to be 0, but there is going to be some kinetic energy at the bottom here, given by 1/2 mv squared. All right, so from conservation of energy, we have the initial kinetic energy plus the initial potential energy minus any work done by friction is equal to final kinetic energy plus the final potential energy. All right, so since it starts from rest, this term is gone. There's no friction, and at the bottom, there's no potential energy. So essentially, we just have UO is equal to K. So UO is going to be mg, right? HO, our starting height, which equals the kinetic energy at the bottom, 1/2 mv squared. All right, so if I was going to solve for velocity or speed at the bottom, it would be simply the square root of 2gho. All right, now let's contrast this with this situation. Suppose we had a ramp. Okay, let's say we had a ramp, and the ramp, let's see, this is the height of the ramp here, and we had a ramp all the way down like this. Okay, so we have a ramp here. So we start the box at the same initial height, HO. Okay, and here's our box here, and it has mass M. So suppose the box in this situation starts at the same height. It's going to come down the ramp here. Okay, pretend this ramp is smooth, and we'll have distance D is the length of the ramp. Distance D. Okay, and it's some HO height, and this here is going to be theta. All right, so now I want to calculate the speed at the bottom down here. Okay, okay, is this speed here the same as this speed over here? Okay, good question, right? So let's go and take a look at that. So if I was going to use kinematics here, okay, let's say I use kinematics, okay, so this is D here, okay. All right, so kinematic equation would be V squared equals VO squared plus 2a, and this is a distance D right here, distance D. Okay, now there is something we have to know here, that this is a triangle, and if you look at the sine of this triangle here, the sine of it, so the sine of theta is going to equal the hypotenuse, which is HO, divided by, excuse me, the side opposite, which is HO, by the hypotenuse, which is D, like this here. Okay, so when you do any ramp problem involving conservation of energy, you have to know this relationship here. Okay, it's going to be critical. Okay, now let's go back to here now. So here's V squared. It starts from rest, so this term is gone. Okay, remember now, as this thing goes in this direction, the acceleration is going to be given as g sine of theta. Okay, g sine of theta. Okay, all right. Okay, remember now, if you forgot where this came from the fact that the parallel force is equal to mg sine of theta, which is equal to ma. And we see the masses cancel out, so a is just g sine of theta. So that's the acceleration going down the ramp. Okay, so again, what is the speed right here? Okay, what's the speed here? Okay, so we go over here. This is v squared. Okay, now we've got to do some substitutions here. This is 2. Okay, the acceleration is going to be g sine of theta times d. Okay, now look over here, this relationship here. Okay, if I was to so HO, right? So let's solve this for HO. So HO is equal to d sine of theta. Okay, there's HO. Now, let's rearrange this equation here a little bit. Let's scroll down a little bit. This is going to be 2. Now, this is going to be G, and this is going to be D sine of theta. All right, now, so here's D sine of theta. Here's also D sine of theta, but that equals HO, the height. So we have here V squared is equal to 2G HO. And voila, V is equal to the square root of 2GHO. So you can solve all ramp problems using the conservation of energy instead of kinematic equations. So this answer here is the same as this answer over here. So the important thing is when doing ramps, make sure you understand that the sine of theta is equal to HO over D. All right, that concludes this short video.